so we need to change this level to 4 meters. We have just one floor, so that's all. We just need level 1 and level 2. And then going to the level 1 plan view, structural plan view, I can draw the grid, and the grids are at 6 meters. So 6,000. And then using the pick lines, place the grid lines. Make sure they are in between the elevation symbols. Just makes it better when you're viewing the model. So that is these are the vertical grid lines, and then we need to also put horizontal. I will just, if I click on modify twice and then change this to A, and then again using the offset and pick lines, this is 9 meters. Okay, now we can show the dimensions. So if you click on the grid, it shows these temporary dimensions. So if you click on the bottom of it, they become permanent. So you can see here the permanent dimension line. And then we can do the same for the vertical. They're appearing a bit small, but that does not matter for now. Okay, so these are the dimensions, and now we can start with the columns. So the Revit file will not be more complex than this one. So we will need to load the family, which we can either do from edit type load, or we can just load family from here. And we need UKC database, but it's a good idea to first, when you load the family, to go up. You see, because I was in a structural framing. So if you are in a structural framing and you try to put the column, it will give you error. So you need to go up a few levels and then make sure you are in the structural columns. Steel, chorus, and now UKC, because this will now work, but otherwise it wouldn't have worked. So this is UKC 203, 203, 100. Yeah, so we loaded now this column, and we can place it at grids. Let's choose the height. We want height, and we want it to go to level 2. And then if I choose add grids and go from right to left, then it's selecting everything that's intersecting. And the columns are placed, so I can just finish. So these are columns done. Next, I can check them in the 3D view. Yeah, okay. Now I need to go to the level 2 and place the beams. And again, I can load the beam. Let me just see what were the secondary beams. I didn't write that. Secondary beams are 254, 146, 31. Okay, so now I can park straightforward. We just place the grid lines, and then place the columns. And now we're going to add the beams, but we need to first load those. So load family, and remember again, we need to go up to the UK folder, and in the UK folder we need to now change from structural columns to structural framing, steel and chorus advanced and UKB. Yeah. And so I can load both of them. The first one is 406178. 67. And the second one is 254 146 31. I'll try to, with the control, to select both of them and load them into the file. Yeah, so we have this one, and the other one is also there. So we have loaded both of them. So when you have secondary beams, you need to load them also in the beam tool. Now, to place these beams, we are in, make sure that you are in the correct level, level 2, so the level of the beams. And then we just can choose on grids, select the grids, and it will place our beams. I didn't click on tag on placement, so I didn't show the tags. But if you click, if I clicked on tag on placement, it would have added the tags. I can add the tags later. So these are my beams, and now I can also add the columns. The secondary beams. So modify, and then beam systems. Automatic beam systems. Here, tag on placement is already selected, so it will put the tags, which is okay. Beam type is 254 146 31, which we have loaded already in the file. And if you look at this here, you can see that there are two secondary beams. So the spacing of secondary beams is 3 meters, because there are three spans. So it's 3000 millimeters. So I can change here to maximum spacing and then 3000. And that will, okay. Yeah, I wanted to have tag style framing. Okay, so Okay, so that these are my secondary beams placed. And then the last thing, let me just check that I put them correctly. Yep. And then the last thing is on level 2, we need to place also, beam system boundary. No. And then the last thing is to place the floor. And basically anything that is made of concrete, usually you will not load, like you load steel sections, but for the concrete elements, you can just modify the existing one. So you can use this floor generic, or you can use this one in situ concrete, although this in situ concrete comes with a screed on top, but you can modify it. The easiest is to just take the generic what was that, Ajiba? I don't know. Anyway, so use the generic and then edit type. So if I click here, edit, the thickness of the floor should be 200. And the floor is concrete. I didn't specify in the example exercise text, but I think it's good to have, well, maybe C35, but you can choose any grade really. Concrete cast in place, C35. You do need to specify the grade because if you don't, that will give you error in robot. And okay. So that is all about the, no, I should, sorry. I basically overwritten the previous types because I should have duplicated. The correct thing would be to duplicate this because otherwise you are overwriting the generic, which is fine. You just I just overwritten it for this file, for this project. So I'll call it 200 millimeter thick C35 slab. And then to place this slab, okay, to place this slab, I can put the height offset. This will make the slab come above the beam. Otherwise, it would be at the same place as the beams. So this will lift the slab on top of the beams. That is what the height offset does. And I can just choose the rectangle and click at 1 point and then click at another. So this is the boundary of the slab, and you don't need to subdivide it. When you transfer it to robot, it will understand that these are 4 different slabs. So one thing that we do need to change before clicking on finish, we need to choose the span direction. Now this is important, so make sure the span direction is correct. What is the span direction of this floor? The floor span in the direction normal to the secondary beams. So the spans are basically in the short direction, in the 3-meter direction, not in the 6-meter. And we are assuming these slabs to all be one-way slabs. So this slab here is spanning in this direction. So if you choose span direction and click on any vertical beam, you will see that now the slab is correctly spanning. So it's spanning in the shorter direction of 3 meters. Frozen. Okay. Yeah. So I will. This is basically it. We'll just also add the pad foundations, and the load, and that's it. So this was the floor. So for the floor, remember, specify the concrete grade and specify the span direction. Okay, and now I'll just go to the level 1 and add the pad foundations. If you don't add the pad foundations, you can still transfer it, but then you will need to add the supports in Robot. Whereas if you add the pad foundations in Revit, it will automatically place the supports. So the footing can be maybe a square one, 1,200 by 1,200 by 450. And in the material, we also need to specify that it's C35 or whichever other grade we want. And then if you click at columns and select all the columns, it will place the pad foundation. So in terms of Revit, this is all that needs to be done. So it's not a long process of modeling, just as well, because you need to also transfer it to Robot and get the results in your test. So this is all really, except we just also need to add the load, and that is in the Analyze tab, Loads, choose the hosted area load, and then here we can change this to live load, and the value in the Z direction is -3. And we just select the slab. So the hosted area load, and then the live load. So this is how we are applying live load. Self-weight will be automatically applied, but the live load we need to add. Of course, if you don't add it in Revit, you can always add it later in Robot, but it's good to have everything done, or pretty much everything. So now, if we haven't already, it's really important to save, because something can go wrong. Transfer moments. You don't need to see this, but you can. Doesn't really say anything. Very. There are no warnings. There is warning. Ah, robot structure analysis regional settings are not set to United States. That's correct. And the others are just some information, so we don't. It doesn't really make any difference. So we can ignore that one and just look at our robot model. Yeah, so this is now it looks a little bit different than when we did the linear ones, beam, truss, and frame. It has this. So here in the layout menu, you only have geometry, properties, and loads. And when you select geometry, you have all the other ones here, so you can change supports from here, or the sections, or apply loads. So you don't need to change it from here. For example, if you want to change the supports, we can actually change the supports. I don't, but let's leave it. Let's leave it for a bit later. So what we have here are 20 beams. We have 9 columns, 1 floor, and then 30 nodes. This. And now we can check our loads. So when you transfer a model from Revit to Robot, it automatically transfers all these various load types, load cases. And I don't need any wind loads, snow loads, accidental loads, temperature, seismic. So I will just delete those ones. But you don't have to do it. You can just leave it there if you don't want to do it. So I just need the dead load and live load to remain. Dead load is the self-weight of the structure, and live load is 3 kilonewtons per meter squared, what we applied in Revit. Now we can also create a load combination. It's this icon here, combinations. I'll call it combination, that's load case 3. And now if you just click dead load and then click here, it will apply factor 1. It doesn't apply the correct one, so we need to put it manually. So 135 is for dead load, and then for live load it will be 1.5. I'm not sure why it does that. It should know that these are the correct factors. So with this, when we click apply, we have created a ULS load combination, ultimate limit state load combination, 1.35 dead load plus 1.5 live load, and then close. And that combination is now added to the list of cases. And so before we do the analysis, we need to make 2 changes to our model. One of these will be in the slab calculation model. So if we go to geometry, and you select the floor here. Click on floor 30. You see the calculation model is shell. So it has certain assumptions, but we want to use the one-way slab, so one-way spanning slab model. I can change the model if I go to geometry, properties, and panel calculation model. And I can create a new type and call it one way spanning slab, for example. And we want no finite elements, and the rest is the same. And make sure here it says one way, so it's one way transfer of loads. So we want this slab to work as one-way slab to transfer load on the beam, assuming the all the load is going on the secondary beams. So this, when I click add, it will add that model, panel calculation model, and then here I can apply it to the selected floor, which is the only floor that we have, numbered 30, and apply. So we have basically changed the type of this floor to one-way spanning slab. And we are doing it really because it will transfer the load as we expect the concrete slab to transfer the load. If you leave it as shell, sometimes we have some odd answers and doesn't behave exactly as we expected. So for our purpose, we need this to work as one-way spanning slab. So that is one modification. One more thing that we need to think about is our beams. We are assuming them when you do your design. You are assuming your beams, secondary beams, primary beams. Normally, you're assuming that to be simply supported. In some cases, you have continuous, but that means that requires the moment connection, and most often the steel structures will just have the simple connections. So let's change our beams so that they have simple connections or pins. And how we can do that is we go to the geometry and release this and choose pinned. And then we need to, so this is what we want. We want all our beams to have pin at both ends, to be simply supported, in other words. And then to apply this to all beams, we can click here and select all of them. Select all of the beams, and then it will come up like this. Or if you see that the beams are numbered from 10 to 29, instead of selecting, you can just type here 10 to 29 and apply. So now we modified our beams to be simply supported. And that is all we need to do in a robot. So we didn't do much in robot. We transferred the load from the structure from Revit, and then we created load combinations, changed the slab model, and changed the beam support type to be simply supported. And now all we need to do is calculate this. It's not giving me any errors, which is good. And then view the results. Results diagrams. What we can check first are the reactions. So we can check the vertical reactions. And these are the reactions from dead load. If I change it to live load, these are the reactions from live load. And if you look at the bottom of this main window, here if you scroll down a little bit, basically Robot gives you the total sum of all reactions for dead load and then also for live load. So you can see that for live load, the sum of vertical reactions is 648. If you know that your building is 6 and 6, 12 meters by 18 meters, so you can then quickly work out the total live load on your structure. So the total live load on your slab is 12 times 18 meters and times 3 kilonewtons per meter squared, which is 648. So it means you're checking that you applied the live load correctly. So the dimensions are correct and the load was correctly applied. You can check the dead load, but then you need to calculate all the weights of the beams and everything. So the live load check is easier. And now we can look at the diagrams. And let's look at the NTM. NTM, we need the vertical forces only. So vertical shear force is Fz and apply. So we have quite a lot of beams here and we have quite a lot of diagrams. So it is a little bit confusing. But if you want to see the shear force diagram on a single secondary beam, then you can select, for example, this beam, any inside secondary beam, because the outside ones will have half of the load of the inside ones. So any inner secondary beam. And then if you click on this edit in new window, it shows that beam and you can rotate the view so you can see the diagram better. We can also change here to the combination and to see the value of the shear force, show the label. So it's showing us that the secondary beam has the shear force of 99 kilonewtons. And the bending moment, My, bending moment is My, is 149 kilonewton meters. So this is our secondary beam. So if you are, for example, doing this and you want to make a report, you can just do the screenshot of this, or there is also something here in robots where you can take snap snapshot. Yeah, yeah, screen capture. Mm, current view and so on. But I don't use it much. I prefer to use the snipping or some other tool for that, just to take the screen grab of this. So now that we know this result from robots, it would be useful to check is our hand calculation going to give us the same value. So maybe you can just try to do for this uh, floor, calculate the load on the slab from dead load and live load using those code parameters 1.35 and 1.5. The concrete you can take as 25 kilonewtons per meter cubed, and try to calculate load on the secondary beam and the shear force and bending moment diagram on the secondary beam by hand calculation. So if you do that, then you can be sure that your robot analysis is correct. (1.35) GK plus 1.5 QK. I don't write Q very well, but you can see. And GK is the self-weight of the slab, and that is the thickness of the slab, which is 0.2 meters times the specific weight of 25. So GK is thickness times specific weight. If you have some other layers, for example, screed, then you would need to add, but don't. So it's just open 2 times 25, and then plus 1.5 times QK, live load, which is 3, and that is 1.5 times 3 is 4.5 plus 1.35 times 5, 1125. So that is design load on the slab. If we now want to find the load on the secondary beam, we know that each meter squared of the slab weighs 11.25 kilonewtons. So we need to find the tributary area for each of the secondary beams. And the tributary area is basically halfway So if this is the whole thing is 3 meters, this is 9 meters. So each span is 3 meters. Each spacing is 3 meters, and that means that if this is halfway and this is halfway, that this tributary area has the width of 1.5 plus 1.5, 3 meters. I'm sure you're doing this in design of elements. So the load on the secondary beam, WSB, is equal to load on the slab times the width. Let's not say the width, times the spacing. Is the spacing really, isn't it, of secondary beams? So that is 11.25 times 3, which is 33.75 kilonewtons per meter. The load on the slab is per meter squared, and on the beam is per meter. Our beam has a span of 6 meters, and the load on it from the slab, the load on it is WSB, which is 33.75 kilonewtons per meter. And the length is 6 meters. We can round it to 34 if you want. And then what will be the reaction on the secondary beam? The reactions are equal to load times length, which is the total load on the secondary beam, divided by 2, and that is 33.75 times 2 times 6 over 2, 33.75 times 3, really. It's 101.25 kilonewtons. So this is, let's say, 101, and this one is 101. Now we can draw the shear force diagram. The shear force diagram for this beam is 101. So you move up 101, then you go down 202, and then up 101. This is the shear force diagram. And the moment on a simply supported beam, maximum moment, is WSB times LSB squared over 8, WL squared over 8, which is 33.75 times 6 squared over 8. The 33.75 times 36 over 8, and that is 152 kilonewton meters. if you, and that moment is obviously a parabola with the maximum value in the middle. Okay, so going back to our robot, we have 148.6. Is that close enough? What do you think? And why do we have a difference? Does anyone want to tell me why do we have the difference? What could be the causing the difference between the results? Any guesses? Rounding. I didn't round though. I. It was. Yeah. Okay. It was 151.9. 151.9. But robot gave us 148.6. And here robot was 99. How much is this in percentages? How would you calculate percentage difference? 151.9 minus 148.6. Let's say divided by 148.6 times 100. So it's about 2.2%. Good, yeah, Memster is right. I ignored the self-weight of the beam, but then should my result be smaller? It's trick. If I add the self-weight, my result will be even bigger. But that's a good point. We did ignore in hand calculation the self-weight of the beam because it's, yes, so we are really, if we add the self-weight of the beam, we will have actually even more difference. But anyway, in your calculations, hand calculations, checks, it's okay to ignore the self-weight because steel beams are going to have a negligible weight compared to the weight applied from the slab. Yeah. Yes. Yeah. Yeah. Concrete. Yeah. So you can see here 24.53 is the assumed self-weight in robot. So if we change our hand calculations and we use this value for the unit weight, then hopefully our results will be closer. But it is a 2% difference, and you can be 2% off in your results. So you can use 25, but just when you use computer, you need to kind of check these properties of material as well. So this was the secondary beam, and now we can also look at. So we can go to end of edit, and now we can look at the primary beam, which is this one, the middle primary beam, and again use edit in new window. and show the parameters. Make sure you change it to the combination. Okay, so it's 202. This is the shear force diagram. And then the bending moment, My, is 603. So this is our primary beam. And now we can also check. We can now also check the vertical load in the column. Obviously, the middle column will have the highest load, and that is Fx, the force in the column, axial force, and then show the parameters. And I can isolate this column to see just that. So the self-weight, the load on this column, vertical force on this column, again, I need to change it to combination, is 610 kilonewtons. 610.6, so 611. And yeah, so these are our results. We can also show the deformation. So we can show the deformation of this. You can see that it's 12 millimeters, or 25 rather, is the biggest deflection of the beams. Sorry, that's from live load, and that is basically what you would be checking. You can check the stresses in the beams, and then you can design also these steel elements as we did in a steel design. You can design the connections between them, and then you can, when you've done all that, you can transfer it back to Revit. So I haven't here looked at the primary beam, but you can see this is the primary beam. This is the primary beam, and this beam has on it the load from the reactions from each of these. So if this is 101, and here 101, and here 101, 101, it means that our secondary beam, primary beam, which is also a simply supported beam, has these loads, 202, 202, and the lengths are 3, 3, 3. And then the shear force, so the reactions are 202, 202, and this is the shear force diagram, 202, 202. This is positive and negative, the shear force. and the bending moment. You can find the bending moment at this point is 202 times 3, so it's 606. Then at this point is the same because of symmetry. So this is the moment diagram. And it is close to what we got from Revit, from robot calculation. And then if we look at the column in the middle, the the column in the middle, this column, it has the reaction of the primary beam, which is 202 on one side. It has 202 from the other side, and then it has these two secondary beams which have 101 and 101. So the reaction, so the force on the column is when you add the reactions of these four beams, columns. So the force in the column is equal to 202 plus 202 plus 101 plus 101, which is 606 kilonewtons. And in robot, it is it was 600 and something. So Fx is the axial force. It was from the combination 610. We ignored the self weight, so our result is a little bit off.